Tonight, we are going to unravel an illusion so deeply embedded in your mind that you don't even realize you are experiencing it. It is happening right now in the quiet spaces between your heartbeats, completely undetected. You are moving through time at a comfortable, invisible speed of 1 second per second. But the universe does not respect your clock. Out there in the deep dark, time is not a river, it is a currency. And the further you travel from this planet, the faster you move, the closer you get to something massive, the higher the cosmic tax becomes. But here is the reality that changes everything you think you know about space exploration. The universe doesn't just slow your watch by a fraction of a second. It isolates you. It can trap you in the future. It can permanently steal your era, your friends, and your entire generation, while you sit in a cabin feeling absolutely perfectly normal. And by the end of tonight, you are going to understand exactly how this temporal prison operates, why the laws of physics demand it, and what it actually means for the first human beings who try to cross the interstellar void. Before we begin, if you find yourself fascinated by the dark and beautiful mechanics of the cosmos, take a second to like this video or subscribe. It is a simple action, but it helps bring this exploration to other curious minds like yours. Now, let's begin. Let's start with the assumption that anchors your entire reality. The assumption of right now. You naturally believe that the exact fraction of a second you are experiencing at this very moment is a universal event, that somewhere out there, a grand cosmic clock is ticking at the exact same rhythm for everyone. A second passing here in your room is the exact same second passing on the desolate surface of Mars, the same second ticking away for a star collapsing in the Andromeda galaxy, the same second that binds all of humanity together. That assumption feels so incredibly obvious it doesn't even feel like a theory. It feels like the bedrock of existence. You trust it the same way you trust gravity to pull you down. You stand on it. It is simply how things are. And yet, that bedrock is a complete fabrication. There is no universal clock. There is no shared now. The present moment you are living in belongs to you and your specific state of motion, and absolutely no one else. To understand how we know this is undeniably true, we have to look at the one thing in the universe that refuses to change: the speed limit of reality. For centuries, classical physics worked perfectly. Isaac Newton gave us a universe that ran like a predictable, beautiful machine. Newton's world made intuitive sense. If you're standing on a train moving 60 miles an hour, and you throw a ball forward at 40 miles an hour, someone standing on the ground watches that ball fly past them at 100 miles an hour. You just add the speeds together. The speed of the object equals your speed plus the object's speed. It works perfectly for trains, cars, bullets, and everything we interact with in everyday life. But then humanity learned to measure light, and light broke the machine. If you are on that same rushing train and you shine a flashlight forward, the light does not travel at its normal speed plus the speed of the train. It doesn't matter if you're walking, flying in a commercial jet, or riding a spacecraft at 99% of the speed of light. The light always pulls away from you at exactly 186,000 miles per second. The universe refuses to let you catch it, and it refuses to let you push it any faster. In the late 1800s, physicists built incredibly sensitive instruments to find a flaw in this. The most famous attempt was the Michelson-Morley experiment in 1887. They assumed the Earth was swimming through an invisible cosmic ocean called the luminiferous ether, which regulated the speed of light. They reasoned that the Earth's movement through this ether should create a drag, changing the speed of light depending on which direction they measured it, like swimming with the current versus against it. They found no difference. None. The speed of light was identically the same in every direction, no matter the time of year, no matter how the Earth was oriented. The ether didn't exist. There was no fixed background to the universe. The implications were terrifying to physicists. If the speed of light is an unbreakable constant, and speed is simply distance divided by time, the math collapses. The equation cannot balance, unless, as a 26-year-old Albert Einstein realized in 1905, you sacrifice the one thing everyone thought was sacred. He followed the logic all the way to its conclusion without flinching. If the speed of light cannot bend, then distance and time must bend instead. Time is not fixed, and what that means for a human body moving through space is the most counterintuitive truth in all of physics. For nearly 2.5 centuries, we lived in a universe that made perfect, undeniable sense. In 1687, Isaac Newton published the Principia Asterisk, and in doing so, he handed humanity the instruction manual for reality. He described a universe that functioned like a magnificent, predictable clockwork mechanism. Gravity pulled, objects fell, and the planets swept through the dark in precise, calculable arcs. But the most important thing Newton gave us was his definition of time. He wrote that absolute, true, and mathematical time flows equably, without relation to anything external. It was a statement of profound comfort. It meant that time was an unyielding, invisible stage upon which the chaos of existence played out. It meant that the universe was fair. A second experienced by a king was exactly the same as a second experienced by a peasant. A second ticking away in a quiet room in London was the exact same second passing in the violent, raging storms of Jupiter. Time was the one thing in the universe that could not be touched, altered, or negotiated with. This Newtonian worldview was so successful, so flawlessly accurate at predicting the motion of cannonballs and comets alike, that it built the entire Industrial Revolution. It was not just a theory, it was the unquestionable bedrock of human sanity. But in the mid-19th century, a Scottish physicist named James Clerk Maxwell began playing with the mathematics of electricity and magnetism. He realized that they were not two separate forces, but two sides of the same coin. When a magnetic field changes, it creates an electric field. When an electric field changes, it creates a magnetic field. They could endlessly fuel each other, leapfrogging through space as a self-sustaining wave. When Maxwell calculated the speed at which this electromagnetic wave would travel, the math produced a very specific, staggering number, roughly 186,000 miles per second. Maxwell immediately recognized that number. It was the known speed of light. Light, he realized, was just an electromagnetic ripple shivering through the dark. It was one of the greatest discoveries in the history of science. But hidden inside this beautiful realization was a fatal flaw, a flaw that would eventually tear Newton's perfect universe to shreds. The problem was simple: waves require a medium. If you drop a stone into a pond, the water ripples. Without the water, there is no wave. If you speak, your vocal cords compress the air in the room, sending a sound wave to someone else's ear. If you pump all the air out of the room, there is absolute silence. A wave is not a physical object. It is a disturbance traveling through a physical medium. So if light is a wave, and we can see the light from distant stars traveling across millions of light years of empty space, what exactly is the light waving through? Physicists could not accept that a wave could travel through pure, empty nothingness. It violated the mechanical rules of reality, and so they invented a ghost. They proposed the existence of an invisible, frictionless, weightless substance that permeated every inch of the universe, filling the void between the stars and the spaces between atoms. They called it the luminiferous ether. The ether was the ultimate background of reality. It was completely stationary. The Earth, the Sun, and the entire Milky Way galaxy were believed to be swimming through this invisible ocean. If you could measure your speed against the ether, you would finally know your true, absolute speed in the universe. In 1887, Albert Michelson and Edward Morley decided it was time to stop theorizing about the ether and actually measure it. Their logic was elegantly straightforward. As the Earth orbits the Sun at roughly 67,000 miles per hour, it must be plowing through this stationary ocean of ether. This should create an ether wind, much like sticking your hand out the window of a moving car. If you shine a beam of light in the exact direction the Earth is moving, the light has to swim upstream against the ether wind. It should be slowed down ever so slightly. If you shine a beam of light perpendicular to the Earth's motion, it is swimming across the current, and its speed should be slightly different. To measure this impossibly small difference, they built an interferometer. It was a masterpiece of precision. They took a massive, heavy block of sandstone and floated it in a circular trough of liquid mercury. This allowed the entire apparatus to rotate smoothly without friction, while insulating it from the vibrations of horse-drawn carriages on the streets of Cleveland, Ohio, outside their laboratory. They split a single beam of light, sent the two halves racing down perpendicular arms, bounced them off mirrors, and brought them back together. If one beam was delayed by even a fraction of a second by the ether wind, the light waves would arrive out of sync, creating a telltale interference pattern. They fired the light, they looked through the eyepiece, and they saw absolutely nothing. The two beams arrived at the exact same instant. Michelson and Morley thought they had made a mistake. They rotated the heavy sandstone block on the mercury and tried again. Nothing. They waited months for the Earth to move to the opposite side of the Sun, changing its direction through space, and ran the experiment again. Nothing. No matter which way they pointed the machine, no matter the season, the speed of light remained exactly, relentlessly identical. 186,000 miles per second. The ether did not exist. Space was a true, dead vacuum. For Michelson and Morley, the experiment was a frustrating failure, but for theoretical physicists around the world, the null result was a nightmare. It wasn't just that the ether was gone, it was what the absence of the ether implied about light. Imagine you are standing on a station platform, and a train rushes past you at 100 miles an hour. Someone on the front of the train fires a laser pointer forward. According to the unbreakable rules of Newtonian physics, the light leaving that laser pointer should travel at 186,000 miles per second, plus the 100 miles an hour of the train. The speed should add up. But the Michelson-Morley experiment proved it doesn't. If you measure that laser beam from the platform, it is moving at exactly 186,000 miles per second. If the person on the rushing train measures the exact same beam, it is pulling away from them at exactly 186,000 miles per second. This makes no logical sense. How can a beam of light travel at the exact same speed relative to two people who are moving at completely different speeds themselves? Physics entered a state of sheer panic. The mathematics of reality were fundamentally broken. For nearly 2 decades, the most brilliant minds on the planet desperately tried to invent mathematical patches to save Newton's universe. The Dutch physicist Hendrik Lorentz and the Irish physicist George Fitzgerald independently proposed an absurd, desperate idea. They suggested that perhaps the ether did exist, but as the Earth moved through it, the physical matter of the Earth and the measuring instruments themselves were being compressed and shrunk by the ether wind. They argued that the interferometer was literally physically shortening in the direction of motion, completely cancelling out the change in the speed of light. They were willing to believe that solid matter magically shrinks simply by moving, all just to avoid the terrifying truth hiding in the math. They were willing to sacrifice the rigidity of space, but they absolutely refused to touch time. Time was sacred. Time was absolute. But the universe does not care about what we hold sacred. The problem was not the measuring instruments. The problem was not an invisible ocean of ether. The problem was the assumption that time was an unchangeable backdrop. The stage was set for a conceptual earthquake. The physics community was staring at a locked door, trying to pick a lock that didn't exist. It would take a mind completely unburdened by the academic dogmas of the era to look at that door and simply walk through the wall next to it. It would take a man who looked at the unbreakable speed limit of the universe and realized that if light refuses to change its speed, then time itself must surrender. In the spring of 1905, the most brilliant physicists in the world were trapped in a state of academic paralysis. The speed of light was an unyielding constant. The equations of classical mechanics were collapsing, and the invisible fabric of the ether had vanished like a ghost. The brightest minds of the era were busy trying to force reality to fit Isaac Newton's centuries-old rules. In Bern, Switzerland, a 26-year-old patent clerk named Albert Einstein was not burdened by these rules. He was not a respected professor. He didn't have access to grand laboratories or expensive interferometers. He sat at a wooden desk, evaluating patent applications for telegraphs and electrical chronometers, and in his spare time he conducted what he called Jedinken experiments, thought experiments. He ran the physics in his mind. Einstein looked at the wreckage of the Michelson-Morley experiment and made a profoundly simple, yet terrifyingly radical decision. He decided to take the universe at its word. If every experiment showed that the speed of light was exactly the same for every observer, regardless of how fast they were moving, then Einstein argued that this was not a math error. It was the fundamental law of nature. The speed of light, 186,000 miles per second, was the cosmic speed limit. It was the one true constant. But Einstein understood the lethal consequence of this assumption. Speed is simply a measure of distance divided by time, miles per hour, meters per second. If the speed of a light beam can never, ever change, then the two things that make up speed, distance and time, must be flexible. They must be able to stretch and compress to keep the speed of light perfectly constant. To make this happen, Einstein had to violently tear down Newton's stage. Space was not an empty, rigid box. Time was not a universal, ticking clock. They were not two separate things at all. They were intimately, physically woven together into a single, four-dimensional fabric. He called it spacetime. You cannot move through space without altering how you move through time. This is the birth of the special theory of relativity, and hidden inside its elegant mathematics is the blueprint for the trap. To understand exactly how the universe steals your time, you do not need complex equations. You only need a simple, imaginary clock. Picture a clock made of light. It consists of two mirrors facing each other, one on the floor and one on the ceiling. A single particle of light, a photon, bounces up and down between these two mirrors. Every time the photon hits the bottom mirror, the clock ticks. Up, down, tick. Up, down, tick. Because the speed of light is perfectly constant, this clock is flawlessly accurate. Now imagine we take this light clock and place it inside a spacecraft made entirely of glass. We put you inside the ship, and we launch you past the Earth at an immense speed, say half the speed of light. Inside the ship, everything feels entirely normal to you. You look at your light clock. You see the photon bouncing straight up and straight down. Tick, tick, tick. Your reality feels perfectly intact. But I am standing on the Earth, looking up at your glass ship, rushing past through the void. What I see is fundamentally different. From my perspective on the ground, your ship is moving forward. Because the ship is moving, the photon inside your clock doesn't just travel straight up and down. As the photon moves up toward the ceiling mirror has moved forward. As it bounces down to the floor mirror has moved forward. From my point of view, your photon is no longer moving in a straight vertical line. It is tracing a long, diagonal zigzag path through space. Here is where the trap snaps shut. The diagonal path the photon is taking from my perspective is physically longer than the straight up and down path you see from inside the ship. Basic geometry dictates that it takes more time to travel a long diagonal line than a short vertical one. In a Newtonian universe, the photon would simply speed up to cover the extra distance, like a baseball thrown from a moving train. But Einstein's rule is absolute. Light cannot speed up. Its speed is universally constant. So if the distance the light has to travel is longer, and the speed of the light cannot increase, there is only one mathematical reality left. The bounce takes longer. From my perspective on Earth, your clock is ticking slower. The space between your seconds has physically stretched. I watch your ship fly by, and I see the universe running in slow motion inside your cabin. This is time dilation. It is not an optical illusion. It is not a mechanical defect in the mirrors. It is the literal geometry of reality adjusting itself to protect the speed of light. And the terrifying part is that this doesn't just happen to a clock made of light. It happens to everything. It happens to the atoms in your body. It happens to the chemical reactions in your cells. It happens to the electrical signals firing across the synapses in your brain. Your heart is just another type of clock. If you're moving at half the speed of light, your heart beats fewer times per hour than mine does on Earth. You age slower. Your biology steps out of sync with the rest of the human race. But the most insidious part of this phenomenon is your own perception. You do not feel like you are in slow motion. Because the neurological processes in your brain have slowed down by the exact same proportion as your clock, your perception of time remains completely unaffected. You pour a cup of coffee, you read a book, you listen to music, and the flow of reality feels absolutely normal. You are living inside a compressed pocket of time, entirely unaware that the rest of the universe is leaving you behind. Why does the universe do this? It helps to think of it as a cosmic budget. Everything in the universe is moving through the 4 dimensions of spacetime at a fixed, combined speed, the speed of light. Right now, sitting in your chair, you are moving very little through the 3 dimensions of space. Therefore, almost all of your cosmic budget is being spent on moving forward through the dimension of time. You are hurtling into the future at the maximum possible temporal speed. But when you get into a spacecraft and hit the throttle, you begin to spend some of that budget on moving through space. You divert your momentum. The faster you travel through space, the less speed you have available to travel through time. If you were to somehow reach the speed of light, a physical impossibility for anything with mass, you would be spending 100% of your cosmic budget on spatial movement. Your movement through time would drop to absolute zero. If you could ride a beam of light, time would completely stop. For a photon, there is no past and no future. The moment it is emitted from a star, and the moment it strikes your eye millions of years later happen at the exact same, instantaneous moment from the photon's perspective. It experiences no time at all. As a human, you can never reach that ultimate speed, but you can get close. And the closer you get, the more severely the math punishes you. The relationship between your speed and the slowing of your time is not a gentle slope. It is an exponential curve governed by a mathematical equation called the Lorentz factor. At everyday speeds, driving a car, flying in a plane, the effect is so infinitesimally small it is entirely meaningless to your biology. You lose fractions of a billionth of a second. But as you push past 50, 60, or 90% of the speed of light, the math becomes violent. You begin to hoard time while the universe around you burns through it. You become a time traveler, locked onto a one-way track into the deep future, entirely cut off from the temporal flow of your origin. When Einstein published this in 1905, the world treated it as abstract mathematics. It was a beautiful, haunting theory that existed only on blackboards and in the imaginations of theoretical physicists. It was too bizarre to be considered a daily reality. After all, human beings cannot run at half the speed of light. We don't notice our clocks behaving strangely. Our intuition screams that Einstein must be wrong and Newton must be right. It is easy to brush this off as a mathematical novelty, a ghost of the equations. But it is not a ghost. It is the invisible architecture of your daily life. The universe does not just apply these rules to hypothetical glass spaceships. It applies them to the dirt beneath your feet. It applies them to the sky above your head. And it applies them to the machines you rely on to navigate your world. If you want to know whether Einstein was right, you don't need to look at a blackboard. You just need to look at the invisible rain of cosmic radiation falling on you right now, and the satellites silently tracking your every move. Because on Earth, the velocity tax is already being collected. It is incredibly tempting to brush off the mathematics of time dilation as a mere theoretical abstraction. When Einstein first published his equations, even the most brilliant physicists of the early 20th century struggled to accept them as a physical reality. It is one thing to draw a diagonal line on a chalkboard and prove that a photon takes longer to bounce between two mirrors. It is an entirely different thing to accept that your own life, your own biology, and your own timeline are subject to this bizarre geometric warping. Our brains simply did not evolve to perceive relativistic effects. We evolved to hunt, gather, and survive in a world where the fastest thing a human being would ever experience was the speed of a falling rock or a galloping horse. At those incredibly slow speeds, Isaac Newton's rigid, unchanging clock works perfectly. But the universe does not confine itself to the limits of human evolution. The proof that time is flexible is not hiding in a distant galaxy. It is raining down on your head, right now, in this exact moment. To see it, you have to look at the invisible ghosts of the upper atmosphere. 10 miles above the surface of the Earth, deep in the freezing stratosphere, our planet is constantly being bombarded by high-energy cosmic rays. These are protons and atomic nuclei ejected from the most violent events in the cosmos: supernovas, collapsing stars, and the feeding disks of active black holes. When these cosmic rays slam into the oxygen and nitrogen molecules of our atmosphere, they shatter them, creating a cascade of subatomic debris. Among this debris is an elementary particle called a muon. A muon is essentially a heavier, highly unstable cousin of the electron, and when physicists say unstable, they mean it possesses a lifespan so brutally short it challenges human comprehension. In a laboratory setting, a muon sitting at rest will decay and cease to exist in approximately 2.2 microseconds. That is 2.2 millionths of a second. When these muons are born 10 miles up in the atmosphere, they are hurled toward the ground at 99.9% of the speed of light. But here is the problem. Even traveling at that astonishing, near-light velocity, a particle that only lives for 2.2 microseconds should only be able to travel about 2,000 feet before it dies. It should disintegrate high in the clouds, long before it ever gets close to the Earth's surface. They should never reach the ground. Yet if you build a particle detector and place it at sea level, it will catch them. It will catch billions of them. They rain down constantly, passing through the roof of your house, through your body, and deep into the crust of the Earth. For decades, this was a baffling anomaly. How could a particle that dies in 2,000 feet travel for 10 miles? The answer is Albert Einstein. Because the muons are traveling at 99.9% of the speed of light, their temporal budget is heavily skewed. From our stationary perspective on the ground, the muon's internal clock is ticking incredibly slowly. While we measure 2.2 microseconds passing on our watches, the muon has barely experienced a fraction of that. Because its time is stretched by its immense velocity, the muon survives for roughly 15 microseconds from our point of view. That temporal stretching gives it exactly enough time to cross the 10 miles of atmosphere and hit the detector. The muon does not know it is living longer. From its own perspective, moving with the particle, exactly 2.2 microseconds pass and then it dies. But from its perspective, the distance it had to travel was physically compressed. Both realities are true. Every single muon that strikes the surface of the Earth is a microscopic time traveler. They do not arrive because of an error in measurement. They arrive because the physics of time dilation dragged them into our future, keeping them alive far beyond their natural expiration date. They are undeniable physical proof that speed slows time. But muons are subatomic particles. It is easy for the human mind to detach from the quantum world. What happens when we scale this up? What happens when we put human-built machines to the test? In October of 1971, a physicist named Joseph Haefel and an astronomer named Richard Keating decided to take Einstein's math out of the laboratory and bring it into the mundane, everyday world. They didn't use a futuristic rocket ship, they used a commercial airline. Haefel and Keating took 4 incredibly precise cesium beam atomic clocks. These are instruments that keep time not with swinging pendulums or vibrating quartz crystals, but by measuring the exact, unvarying electromagnetic resonance of cesium-133 atoms. They are so accurate they would not lose a single second in millions of years. The scientists bought plane tickets. They strapped these atomic clocks into the first-class seats of a Pan Am Boeing 747, and they flew them eastward, entirely around the world. Then they took the same clocks and flew them westward, again circling the globe. Imagine the scene. Ordinary passengers were sitting in the cabin, drinking coffee, reading newspapers, complaining about turbulence, completely oblivious to the fact that the men sitting a few rows away were actively testing the fabric of reality. When Haefel and Keating finally landed back in Washington, D.C., they took the flying atomic clocks and compared them to identical atomic clocks that had remained stationary at the United States Naval Observatory. If Newton was right, the clocks would match perfectly. A second in the sky should be a second on the ground. They did not match. The clocks that flew eastward, moving in the same direction as the Earth's rotation, and therefore moving faster relative to the center of the Earth, had ticked slower. They had lost about 59 nanoseconds. The clocks that flew westward, moving against the Earth's rotation, effectively moving slower relative to the Earth's center, had ticked faster. The difference was microscopic, billionths of a second. You could never feel it, but the atomic clocks felt it. Haefel and Keating did not just prove time dilation, they confirmed Einstein's equations with haunting precision. The time lost by the flying clocks exactly matched the mathematical predictions of special relativity. The passengers on those flights actually stepped off the planes slightly younger than the people waiting for them at the baggage claim. They had mechanically, literally time traveled. This experiment cemented a terrifying truth. Time dilation is not a fringe theory. It is a fundamental property of engineering. And if you think this still doesn't affect your daily life, you need to reach into your pocket and look at your smartphone. Right now, hovering roughly 12,500 miles above your head, is a network of 31 active global positioning system satellites. Every time you open a map application, order a rideshare, or track a delivery, your phone is silently communicating with these machines. Inside each of those satellites is an atomic clock. Your phone calculates your exact position on Earth by measuring exactly how long it takes for a radio signal to travel from multiple satellites down to your device. Because those radio signals travel at the speed of light, the timing has to be flawless. An error of a single microsecond, 1/1,000,000th of a second, would throw your location off by nearly 1,000 feet. But here is the problem. Those GPS satellites are orbiting the Earth at approximately 8,700 miles per hour. Because they are moving that fast, special relativity dictates that their onboard clocks must tick slower than the clocks resting on the surface of the Earth. According to the math, the velocity of the satellites causes them to lose about 7 microseconds every single day. 7/1,000,000ths of a second sounds like nothing, but at the speed of light, a 7 microsecond delay translates to a tracking error of about 1.3 miles. If GPS engineers ignored Albert Einstein, that error would compound every single day. Within 48 hours, your navigation app wouldn't just put you on the wrong street, it would put you in the wrong city. Within a week, the entire global logistics network, airplanes, cargo ships, military drones, and emergency services would completely collapse. To prevent this, the engineers who build GPS satellites have to actively manipulate time. Before the satellites are ever launched into space, their atomic clocks are deliberately tuned to run slightly fast. They are programmed to tick at an incorrect rate on the ground, so that once they are blasted into orbit and reach 8,700 miles per hour, the universe's velocity tax kicks in, slowing the clocks down just enough to perfectly synchronize with the Earth. Every time you navigate to a coffee shop, you are relying on the fact that time flows at a different speed in space. Time dilation is not abstract philosophy, it is infrastructure. The most precise positioning technology in human history is built entirely on the premise that the cosmic clock is a lie. Velocity warps reality. The faster you move, the more time you lose. But velocity is only half of the equation. It is the part of the trap that requires you to move. It requires engines, thrust, and momentum. If you simply stand still, you might think you are safe from the temporal warping of the universe. You are not. Because in 1915, Einstein returned with a second revelation. A realization so dark, so heavy, and so inescapable, it proved that the universe doesn't even need you to move to steal your time. It just needs you to exist near something heavy. Speed is the bait, but gravity is the chain. For a decade after publishing his special theory of relativity, Albert Einstein was haunted by a single glaring omission. His 1905 equations worked perfectly for objects moving at constant speeds in a straight line, but the real universe is rarely that simple. Things accelerate, things fall, and looming over all of this motion was Isaac Newton's oldest, most untouchable ghost, gravity. Newton had described gravity as a mysterious, invisible tether, a force that reached across the vast, empty dark of space to instantly pull objects together. The sun pulls the earth pulls the apple. It was mathematically brilliant, but Newton himself admitted in his private letters that he had absolutely no idea how it actually worked. The idea that matter could act upon other matter across an empty vacuum without any physical contact seemed absurd even to the man who wrote the equations. Einstein decided to answer the question Newton couldn't, and in 1915, he published his general theory of relativity. In doing so, he didn't just update gravity, he completely eradicated it as a force. Gravity, Einstein declared, does not exist in the way we think it does. It is not a magnetic pull, it is a geometric trap. To understand the sheer, terrifying weight of what this means, you must return to the concept of spacetime, the four-dimensional fabric that weaves space and time into a single, unified stage. Imagine this fabric as a taut, perfectly flat trampoline. If you roll a marble straight across it, the marble moves in a flawless, unbending line. But if you take a massive, heavy bowling ball and place it right in the center of the trampoline, the fabric sags under its weight, creating a deep, curved depression. If you try to roll the marble now, its path is no longer straight. It curves, spiraling down along the slope toward the heavy mass at the center. The bowling ball isn't reaching out with an invisible force to pull the marble. The marble is simply following the natural, warped geometry of the space it is moving through. The Earth revolves around the Sun, not because the Sun is pulling it, but because the Sun is so unimaginably massive that it has carved a colossal trench into the fabric of the universe. The Earth is endlessly rolling along the curved slope of that cosmic trench. This is a beautiful, elegant way to understand why planets orbit. But remember, the fabric is not just space. It is space * time *. When a massive object warps the fabric of the universe, it doesn't just stretch physical distance. It severely stretches the flow of time. This is the rule of gravitational time dilation. The deeper you sit inside one of these gravitational dents, the closer you are to a massive object, the slower your time runs compared to someone standing further away in flatter space. You do not need to be hurtling through the void in a glass spaceship at near light speed to lose your time. You just need to be near something heavy. Gravity is not just the phenomenon that keeps your feet on the floor. It is a temporal anchor, actively dragging your clock to a crawl. This means the cosmic trap is entirely inescapable, even in the safety of your own home. Right now, as you sit reading or listening to this, time is not passing at the same rate across your own body. Because the Earth is a massive object, it bends space-time. And because you are standing on its surface, you are sitting at the bottom of its gravitational gravity well. The pull of gravity is infinitesimally stronger at your feet than it is at your head, simply because your feet are an inch or two closer to the dense core of the planet. Therefore, time is physically running slower at the floor than it is at the ceiling. It sounds like an absolute absurdity, a mathematical technicality that could never be measured in the real world. But the universe is relentless in enforcing its rules. In 1959, two physicists named Robert Pound and Glenn Ribcad decided to prove it. They didn't use rockets or satellites, they used a stairwell. Inside the Jefferson Physical Laboratory at Harvard University, there was a brick tower reaching 74 feet high, roughly the height of a 6-story building. Pound and Ribcad placed a highly sensitive emitter of radioactive gamma rays in the basement and a precision detector at the top of the tower. Gamma rays act like tiny, incredibly fast-ticking clocks. They vibrate at a very specific frequency. If time truly ran faster at the top of the tower than at the bottom, then the gamma rays climbing up against the Earth's gravity would appear to slow down from the perspective of the detector at the top. The frequency of the light would physically stretch, shifting toward the red end of the spectrum, a phenomenon known as gravitational redshift. The predicted difference in the flow of time across a mere 74 feet of altitude was so infinitesimally small, a fraction of a trillionth of a percent, that detecting it was considered a fool's errand. It required measuring a shift equivalent to the width of a single atom. Yet they found it. Exactly as Einstein's math demanded. Even across the height of a brick building on a university campus, gravity visibly, measurably bent time. You are existing in a temporal gradient right now. Your feet are genuinely, physically younger than your mind. Over the course of an 80-year lifespan, your head will age a few billionths of a second more than your shoes. The difference is biologically irrelevant to a human being, but conceptually, it is staggering. It means there is no sanctuary from relativity. Everywhere you go, every breath you take, the geometry of the universe is subtly manipulating the rate at which you experience reality. But the Earth is a rocky, gentle world. Its gravitational grip is incredibly weak on a cosmic scale. Our planet barely makes a dimple in the fabric of spacetime. The time dilation you experience here is just a whisper, a microscopic rounding error in your lifespan. If a simple brick tower in Massachusetts is enough to physically distort the flow of time, what happens when we leave this quiet solar system? What happens when we approach the true monsters of the cosmos, objects so unimaginably dense and terrifyingly heavy that they don't just bend the fabric of spacetime, they rip it wide open? Because out there in the deep dark, gravity isn't just a force that makes your feet younger. It is a force that can freeze you in time, entirely, forever. To truly understand the terrifying power of time dilation, we must leave the safety of our solar system. The Earth, the Sun, and the planets we know are gentle, quiet things. Their gravitational pulls are minor indentations in the fabric of spacetime. To see what relativity looks like when the universe stops playing by the rules of human comfort, we have to travel to the cosmic graveyard. We have to look at the monsters left behind when giant stars die. When a star roughly 10 to 20 times the mass of our Sun reaches the end of its life, it runs out of the nuclear fuel required to keep it burning. For millions of years, the outward explosive pressure of nuclear fusion has been perfectly balanced against the inward crushing weight of the star's own immense gravity. But when the fuel is gone, the fusion stops. In a fraction of a second, gravity wins. The outer layers of the star collapse inward at a significant fraction of the speed of light, hit the dense core, and rebound in one of the most violent explosions in the universe, a supernova. But what remains in the center is where physics descends into madness. The core of the star is crushed by a gravitational force so unimaginably extreme that the empty space inside its very atoms is squeezed out of existence. Protons and electrons are violently smashed together to form neutrons. The entire core, once millions of miles across, is compressed into a perfectly smooth, furiously spinning sphere no larger than a small city, perhaps 10 or 12 miles across. This is a neutron star. It is the densest physical object in the known universe. The density of a neutron star is so severe that it breaks the human mind's ability to conceptualize weight. If you were to take a standard teaspoon and scoop up a single spoonful of neutron star material, that tiny amount of matter would weigh roughly 10 million tons on Earth. You are holding the mass of a massive mountain, compressed into a space the size of a sugar cube. Because of this absurd density, the surface gravity of a neutron star is hundreds of billions of times stronger than the gravity pulling you down into your chair right now. This is not just a dent in the fabric of spacetime. It is a sheer, terrifying cliff. Imagine, through some impossible feat of science fiction technology, you could stand on the surface of a neutron star without being instantly atomized by the pressure and the magnetic fields. As you stand there, looking up at the universe, you're sitting at the absolute bottom of a crushing gravitational well. According to general relativity, because the gravity is so intense, your time must run drastically slower than the time of the universe above you. On the surface of a neutron star, time runs at roughly 70% the rate of normal flat space. For every single second you experience, your heart beating normally in your chest, almost 1.5 seconds pass in the vast emptiness of the cosmos. If you stood on that dead star and looked through a telescope at Earth, you would not see the universe moving normally. You would see the universe in fast forward. you would watch planets whip around their stars at unnatural speeds. You would watch the cosmos accelerating toward its inevitable death, all while you remain perfectly, quietly preserved in your slow-motion bubble. But a neutron star, as terrifying as it is still a physical object. It has a hard surface, it has a physical limit. It is a monster, but it is a monster we can still understand. What happens when a dying star is even heavier? What happens when a star is 30, 40, or 50 times the mass of our Sun, and its core collapses? In that scenario, not even the quantum mechanical resistance of neutrons can withstand the crushing weight of gravity. The collapse does not stop at the size of a city. It does not stop at the size of a basketball. It does not stop at all. The matter simply keeps falling inward, crushing infinitely down upon itself, until all the mass of a giant star is concentrated into a single, dimensionless point of infinite density. A singularity. Gravity has pulled so hard that it has fundamentally ripped a hole in the fabric of spacetime. What forms around this tear is a region of space where gravity is so overwhelmingly powerful that the escape velocity, the speed required to break free from its pull, exceeds 186,000 miles per second. It exceeds the speed of light. And since nothing in the universe can travel faster than the speed of light, nothing can escape. Not matter, not radiation, not information, and certainly not you. This boundary, the absolute point of no return, is called the event horizon, and the object it surrounds is a black hole. Black holes are often described as cosmic vacuum cleaners, swallowing everything that gets too close. But that description misses the true, existential horror of what a black hole actually is. A black hole does not just consume light, it consumes time itself. To understand the ultimate temporal trap, we have to conduct a thought experiment. Imagine you are safely orbiting in a spaceship, a few million miles away from a supermassive black hole. Your friend volunteers to put on a spacesuit, step out of the airlock, and fire their thrusters, falling directly toward the event horizon. You sit in your ship, watching them through a powerful telescope. At first, everything looks normal. They are falling, accelerating as the black hole's gravity pulls them in. But as they get closer to the event horizon, the gravity well becomes exponentially steeper. And as the gravity grows stronger, the time dilation becomes increasingly severe. From your perspective, sitting safely in flat space, your friend's clock is slowing down. You watch them wave their hand, but the wave seems sluggish, like they are moving through thick molasses. As they get closer to the black line of the horizon, their movement slow to a crawl, but something else is happening to them. The light bouncing off their spacesuit is struggling to climb out of the black hole's gravitational well to reach your telescope. As the light fights against the crushing gravity, it loses energy. It stretches out, its wavelength becoming longer and longer. This is gravitational redshift. Because of it, you watch your friend's spacesuit turn from white to yellow to deep crimson red. As they touch the very edge of the event horizon, time dilation reaches infinity. From your perspective, time for your friend completely stops. You never actually see them cross the event horizon. They simply freeze, perfectly suspended on the edge of the abyss, turned a dark, bloody red. And then, as the light stretches further into the infrared and microwave spectrums, they slowly, quietly fade into nothingness. To you, they are a frozen ghost, forever trapped on the edge of the universe. But that is just your perspective. What does your friend experience? From their point of view inside the spacesuit, nothing slows down at all. Their heartbeat is normal. They don't feel themselves freezing. If it is a supermassive black hole, the tidal forces at the event horizon are surprisingly gentle. They wouldn't even feel a physical bump. They simply drift right through the event horizon and into the darkness. But if your friend were to look back over their shoulder, out away from the black hole and into the universe they are leaving behind, they would see a terrifying sight. Because their time is slowed to a near halt, the time of the outside universe is running incredibly fast. As they fall into the dark, they would watch the stars above them rapidly burning out. They would watch galaxies spin and collide in the blink of an eye. They would watch the entire future of the universe play out in blinding fast forward. They are effectively watching the universe die. Once they cross the event horizon, the trap is absolute. The geometry of spacetime inside a black hole is warped so severely that space and time literally swap roles. In your normal life on Earth, you can move freely through space. You can walk left, right, forward, or backward, but you're forced to move forward through time. You cannot stop time, and you cannot walk into the past. Inside the event horizon, the singularity, the infinitely dense point at the center, is no longer a location in space. It becomes a point in time. It becomes your absolute, unavoidable future. Just as you cannot prevent tomorrow from arriving on Earth, you cannot prevent yourself from reaching the singularity inside a black hole. No matter how hard you fire your engines, no matter which direction you turn, every single path, every possible geometric trajectory leads directly to the singularity. You are no longer falling through space. You are being dragged forward through time, and the singularity is the end of time itself. A black hole is the universe's ultimate prison. It severs you from the timeline of reality and locks you in an inescapable temporal pocket, where the only exit is the cessation of existence. It is the most terrifying manifestation of Einstein's equations. It proves that the universe possesses the mechanical capability to absolutely, permanently divorce a human being from the flow of history. But you don't need to fall into a black hole to suffer the agonizing consequences of relativity. You don't need to visit a collapsed star to become a chronological orphan. The tragedy of time dilation does not require cosmic monsters to ruin a human life. It only requires us to do exactly what we have dreamed of doing since we first looked up at the night sky. It only requires us to build a fast ship and try to touch the stars. Ever since humanity first understood that the twinkling lights in the night sky were not holes in a cosmic canopy, but entire, distant suns, we have been obsessed with reaching them. Science fiction is built entirely upon this dream. We imagine grand starships, warp drives, and faster-than-light travel, allowing intrepid explorers to hop between galaxies as easily as catching a flight across the Atlantic. We envision a future where humanity is an interstellar species, connected across the vast, terrifying emptiness of space by communication and trade. But science fiction lies to us. It lies by conveniently ignoring the brutal, uncompromising mathematics of Albert Einstein. The universe is not a playground waiting to be easily conquered. The distances between the stars are so incredibly vast that they mock the human lifespan, and the only physical way to cross those distances before dying of old age is to travel at a significant fraction of the speed of light. But as we now know, speed demands a toll, and this toll creates a paradox so deeply unsettling that it took physicists decades to fully accept its implications. To understand the agonizing human cost of interstellar travel, we must confront what is famously known as the twin paradox. Imagine two identical twins born on the exact same day. We will call them Mark and Scott. They share the same DNA, the same biology, and the same quiet timeline on Earth. When they are 25 years old, Scott volunteers for humanity's first interstellar mission. He boards a highly advanced spacecraft designed to travel to a star system 10 light-years away. Scott's ship is capable of incredible speed. He accelerates until he is traveling at 86.6% of the speed of light. According to the rules of special relativity, because Scott is moving so fast, his time must slow down relative to his brother Mark, who remains stationary on Earth. At 86.6% of light speed, the Lorentz factor, the mathematical curve that dictates time dilation, tells us that Scott's time is running at exactly half the speed of Earth's time. For Scott inside the ship, everything feels completely normal. He reads books, exercises, and watches the stars blur past his window. From his perspective, the journey to the star system 10 light-years away takes him roughly 5 years. He arrives, orbits the star, takes his measurements, and immediately fires his engines to return home, traveling at the exact same speed. The return trip takes another 5 years of his time. When Scott's ship finally decelerates and lands back on Earth, he opens the hatch. He has aged exactly 10 years. Biologically, physically, and mentally, he is 35 years old. He looks out at the crowd, searching for his twin brother. He expects to see a 35-year-old man. Instead, he finds an elderly man, 65 years old, with gray hair and wrinkled skin, leaning heavily on a cane. Mark has aged 40 years. Scott has aged 10. The twins are no longer twins. The fundamental symmetry of their lives has been violently, permanently broken. For decades, people argued that this was a logical contradiction. They claimed it was a paradox that disproved Einstein's entire theory. Their argument was based on a very simple premise. Relativity states that all motion is relative. If you're sitting in a train and another train passes you, you can't tell if you're moving forward or if the other train is moving backward. There is no absolute stillness in the universe. Therefore, from Scott's perspective inside the spaceship, he isn't moving at all. He feels perfectly stationary. To Scott, it is the Earth that is moving away from him at 86.6% of the speed of light. And if the Earth is the thing moving, then shouldn't Mark's time slow down? Shouldn't Mark be the one who is younger when they reunite? How can the universe possibly decide which twin actually ages slower, if both twins see the other one moving? The resolution to this paradox is elegant, and it is entirely grounded in the physical reality of the universe. The situation is not symmetrical. There is one crucial, undeniable difference between the two brothers. Mark, sitting on Earth, remained in a single, unaccelerated frame of reference the entire time. He never felt a physical force pushing him into his chair. He just sat there. Scott, however, had to fire engines. He had to accelerate to near light speed, feeling the crushing g-force of that acceleration. When he reached the distant star, he had to fire his engines again to violently decelerate, turn the ship around, and accelerate back toward Earth. Scott felt the physical force of changing his speed and his direction. Acceleration is not relative. It is absolute. You can feel it. When you are in a car and someone slams on the brakes, you are thrown forward against the seatbelt. You know without a shadow of a doubt that you are the one changing speed, not the world outside. Because Scott is the one who accelerated, decelerated, and changed his frame of reference, he is the one who steps out of the normal flow of time. He is the one who takes the geometric shortcut through spacetime. The universe mathematically registers his acceleration, and it collects the velocity tax from his biology. The twin paradox is not a paradox at all. It is a terrifying, guaranteed promise. If you leave Earth, travel fast, turn around, and come back, you will be younger than the people you left behind. Always. This isn't a thought experiment anymore. We have already done it. In 2015, NASA conducted a year-long mission aboard the International Space Station. They sent astronaut Scott Kelly into orbit for 340 days, while his identical twin brother, Mark Kelly, remained on Earth. Scott traveled at roughly 17,500 miles per hour for nearly a year. When he returned to Earth, scientists meticulously measured his biology against his brother's. Because the speed of the ISS is relatively slow compared to the speed of light, the time dilation was incredibly small, but it was real. Scott Kelly came back from space roughly 5 milliseconds younger than his twin brother. 5 milliseconds is a rounding error. It is a blink of an eye. You cannot feel it. But what happens when we scale the math up? What happens when humanity finally builds an engine capable of true interstellar speeds, and we send a crew to explore a distant part of the galaxy? Imagine a ship traveling at 99.99% of the speed of light. At this speed, the Lorentz factor climbs to a staggering 71. This means that for every single year the crew experiences on the ship, 71 years pass on Earth. A crew of 25-year-old astronauts leaves Earth on a mission that will take exactly 10 years of their time. They say goodbye to their parents, their siblings, and their newborn children. They launch into the dark, watching the stars streak past. They explore, they run their experiments, and they return home. They have aged 10 years. They are 35 in the prime of their lives, excited to share what they have found with the world. But as they decelerate and approach Earth orbit, the radio is silent. The communication protocols they knew are obsolete. The orbital infrastructure is unrecognizable. They step out of the ship, and the crushing weight of relativity finally hits them. 710 years have passed on Earth. Everyone they ever knew, their parents, their spouses, the newborn babies they held in their arms before launch, has been dead for 6 centuries. The civilization that built their ship is a distant historical memory. The languages have changed. The nations have fallen and risen again. The Earth they return to is not the Earth they left. It is an alien world, populated by strangers who view the astronauts as ancient ghosts who have miraculously stepped out of the past. They didn't just miss a few birthdays. They missed entire eras of human history. They missed wars, revolutions, and the slow, beautiful evolution of society. They are permanently, irrevocably severed from their own timeline. This is the agonizing human cost of time dilation. We dream of conquering the stars, but the universe demands that we pay for that conquest with our isolation. If we ever venture out into the deep dark at the speeds required to cross the void, we must accept that every journey is a one-way trip into the future. We can explore the galaxy, but we can never truly come home. We can only arrive at whatever the future has become while we were away. We become chronological orphans, forever wandering a universe that refuses to wait for us. But the tragedy of interstellar travel is only a symptom of a much deeper, more unsettling truth. The isolation of the astronauts forces us to confront a question that philosophers and physicists have debated for a century, a question that threatens to break our very understanding of existence. If a spaceship can travel hundreds of years into the future while only experiencing a decade, then what exactly does the word "now" even mean? We often think of interstellar travel as a purely engineering problem. We assume that if we can just figure out how to build a strong enough hull, design a powerful enough engine, and generate enough energy, the stars will finally be ours. We view the universe as a vast, dark ocean, and we are simply waiting to build a fast enough ship to sail it. But the universe is not an ocean, it is a geometric web. And the mathematics that govern this web do not care about our engines or our ambition. To understand how this web tightens around you, you have to look at the invisible mathematical curve that dictates the flow of time in our universe. It is called the Lorentz factor. Named after the Dutch physicist Hendrik Lorentz, this equation is the absolute, unyielding judge of how much time you will be allowed to keep when you travel through space. The Lorentz factor is not a straight line. If it were a straight line, space travel would be manageable. If you doubled your speed, you would simply lose twice as much time. It would be a fair trade, but the universe is not fair. The Lorentz factor is an exponential curve. It starts off entirely flat, barely registering your movement. As you accelerate to 10, 20, or 30% of the speed of light, the curve barely creeps upward. The time dilation you experience is minuscule. But as you push the throttle past 50%, the curve begins to steepen. At 80%, it ramps up sharply, and as you push into the 90s, approaching the absolute speed limit of reality, the curve violently, almost vertically, spikes toward infinity. This mathematical curve is the anatomy of a tragedy. It is the exact formula for how a human being becomes a ghost. Let us translate this equation into the grim reality of a human life. Imagine we build a spacecraft capable of maintaining relativistic speeds, and we aim it at Proxima Centauri, the closest star system to our Sun. It sits roughly 4.24 light-years away. To the cosmos, this is our next-door neighbor. To us, it is a staggering 25 trillion miles away. You are 30 years old. You say goodbye to your spouse, who is also 30, and your 5-year-old daughter. You step onto the ship, and you accelerate to 50% of the speed of light. At this speed, the Lorentz factor is relatively forgiving. It sits at about 1.15. From the perspective of your family on Earth, it takes you 8.5 years to reach the star, and another 8.5 years to come back. To them, 17 years pass. But inside your cabin, moving at half the speed of light, the math protects you slightly. You experience roughly 14.5 years of total travel time. When you land back on Earth, you are 44 years old. You step out of the ship and your spouse is 47. Your daughter is 22. The gap is jarring, but it is survivable. You have aged a little slower and they have aged a little faster. You missed 2.5 years of their lives. You missed a few birthdays, a few holidays, perhaps the subtle graying of your partner's hair. You feel a sudden, sharp pang of disconnection, but with time you can bridge the gap. You can catch up. But humanity is rarely satisfied with going slow. If we have the technology to reach the stars, we will want to reach them faster. So let us rerun the exact same mission to the exact same star, but this time, you push the engines to 90% of the speed of light. At 90%, the Lorentz factor jumps to 2.3. The mathematical slope is steepening. You become significantly detached from the flow of time on Earth. From the perspective of mission control, your ship crosses the distance faster. The round trip takes about 9.5 years, but inside your ship, time has been severely compressed. For you, the entire journey to Proxima Centauri and back takes just over 4 years. You leave Earth at 30 and you return at 34. You step out of the airlock, expecting to see the world much as you left it. But your spouse is nearly 40. Your 5-year-old daughter is now a 14-year-old teenager. You are no longer dealing with a small gap in time. You have missed nearly a decade of human experience. You did not see your daughter learn to ride a bike. You did not comfort her during her first heartbreak. You did not experience the quiet, mundane Tuesday evenings with your partner that slowly build the foundation of a marriage. You have returned physically vibrant, youthful, and full of energy, but you are standing in a living room that feels like a museum. You are a stranger who has fast-forwarded through the formative years of your own family. And still, the math has not revealed its true cruelty. Let us push the ship to the absolute bleeding edge of physics. You accelerate to 99.99% of the speed of light. you are skimming the very limit of reality. At this velocity, the Lorentz factor detonates. It skyrockets to an astonishing 70.7. You are no longer just traveling through space, you are severing your tether to the human timeline entirely. From the perspective of the Earth, the round trip takes 8.5 years. But for you, inside the ship, the distance between the stars physically contracts. The space compresses, and your time slows to an agonizing crawl relative to the outside universe. For you, the entire round trip to a star system 25 trillion miles away takes 44 days. 44 days. You leave in the middle of summer. You spend 6 weeks in the quiet hum of your spacecraft. You read a few books. You run a few system checks. You turn the ship around, and you come home before autumn has even finished shedding its leaves from your perspective. You land on Earth. You are still 30 years old. You have barely grown a beard. But 8.5 years have passed outside your window. Your spouse is 38. Your daughter is 13. You look at them and your mind violently rejects the reality in front of you. Just 6 weeks ago, from your perspective, your daughter was a toddler holding your hand at the launch pad. Now she is a teenager who barely remembers the sound of your voice. You left a young partner, and you have returned to someone approaching middle age, someone who had to learn how to live without you, who had to mourn your absence, and who built a completely new life while you were suspended in the dark. You have essentially vanished from existence, only to reappear out of thin air almost a decade later, completely unchanged. This is where we must confront a truth that the mathematical equations cannot adequately convey. Age is not just a biological metric. It is not just the graying of hair, the slowing of a metabolism, or the tally of cell divisions. Age is a ledger of shared context. It is the slow, relentless accumulation of experiences, tragedies, joys, and mundane moments that shape how a human being understands the world. When you travel near the speed of light, you do not just skip the biological aging process, you skip the context. The people who remained on Earth lived through years of shifting politics, changing art, new music, and collective societal grief. They endured natural disasters, economic shifts, and the slow evolution of human culture. They adapted, they changed their minds, they formed new opinions based on years of experiences that you simply did not have. When you return, you are a time capsule. You are carrying the cultural assumptions, the vocabulary, and the emotional baseline of a world that no longer exists. You stand at the arrival gate, and the world looks familiar, but the invisible threads of connection have been permanently severed. You share the same space with the people you love, but you no longer share the same when. You are a biological 30-year-old with the life experience of a 30-year-old, trying to interact with a 38-year-old who has lived through a decade of life you simply slept through. There is no word in the human language for this specific type of loneliness. It is an isolation born not of distance, but of chronology. You can close the physical distance by flying back to Earth, but you can never, ever fly back in time to recover the context you lost. The universe allowed you to cross 25 trillion miles in 44 days, but it charged you 8 years of your family's life to do it. And that is just the cost of a journey to our closest neighboring star. If humanity ever decides to reach deeper into the galaxy, to travel hundreds or thousands of light years to find new, habitable worlds, the Lorentz factor guarantees that no explorer will ever return to the world that sent them. The gap will not be measured in years or decades, but in centuries and millennia. The explorers who push into the deep Milky Way will return to an Earth where their names are either completely forgotten or written in ancient history books. They will be relics. But what happens when it isn't just a single ship of explorers? What happens when humanity decides that the Earth is no longer enough? and we attempt to move an entire society across the stars. If we cannot reach the speed of light, we will be forced to travel slower, condemning generations to live and die in the empty dark between the suns. This brings us to the ultimate, most agonizing consequence of the interstellar void. The tragedy does not stop with a single astronaut outliving their family. It scales up. It infects entire populations. Because when you put a society in a box and hurl it across the universe, the trap of time and distance creates a completely different kind of monster. If we accept the brutal reality that traveling near the speed of light is mathematically guaranteed to sever us from our timeline, and that reaching the absolute speed of light is physically impossible, humanity is left with a daunting realization. If we want to colonize the stars without violently tearing families apart across centuries of time dilation, we have to travel slower. Much, much slower. We have to accept that the journey will take longer than a single human lifespan, and that realization inevitably leads to one of the most persistent and melancholic concepts in the history of space exploration, the generation ship. A generation ship is not a vehicle, it is a mobile world. It is a colossal, self-sustaining arc designed to travel across the interstellar void at a fraction of light speed, perhaps just 5 or 10%. At that speed, the Lorentz factor is gentle. The time dilation is negligible. A year on the ship is roughly a year on Earth. The temporal trap seems to have been bypassed. But the trap has merely changed its shape. At 10% of the speed of light, a journey to a star system just 50 light-years away would take 500 years. The people who build the ship, the engineers who design the life support systems, and the brave crew who stand on the launch pad and wave goodbye to Earth will never see the destination. They will live out the remainder of their natural lives entirely within the metal confines of the hull. They will die in the dark space between the stars. Their children will be born on the ship. These children will learn to walk on synthetic decks. They will learn about Earth from digital archives, viewing the blue oceans and green forests as abstract concepts, like myths from a forgotten age. They will grow old, and they too will die in the dark. Their grandchildren, and perhaps their great-grandchildren, will repeat this cycle. Generation after generation, born into a steel cylinder, inheriting a mission they did not choose, traveling toward a planet they cannot fully comprehend. When the ship finally decelerates 500 years later, and the 5th or 6th generation of descendants looks out the window at their new sun, they will not be the people who left Earth. And Earth will not be the planet that sent them. This is where the generation ship concept reveals its deep, sociological horror. The people who step off that ship and onto the virgin soil of a new world will be chronological orphans of a completely different kind. They will not be time travelers who skip centuries. They will be the isolated, mutated remnants of a culture that no longer exists. Imagine a ship launching from Earth today. The crew carries with them the language, the politics, the music, and the moral values of the 21st century. For 500 years, that culture is locked inside a closed system. It will inevitably drift. Words will change meaning. Social structures will adapt to the brutal realities of living on a spacecraft where resources are strictly controlled. The original mission might morph into a religious doctrine. The memory of Earth might fade from a historical fact into a sacred legend. Meanwhile, back on Earth, 500 years of unconstrained human history will march forward. Think about the Earth 500 years ago. The year was the early 1500s. The Renaissance was in full swing. The printing press was a new invention. The concept of electricity was unimaginable. If a ship had launched in 1500 and arrived today, the crew stepping off that ship would be speaking a version of English we could barely understand. Their medical knowledge would be based on balancing bodily humors. Their political beliefs would be anchored in absolute monarchy and divine right. They would be completely, utterly alien to us. When the generation ship from our time finally arrives at its destination in the year 2500, and they attempt to establish a communication link with Earth, the response they receive will be from a civilization that has evolved past them. The Earth of 2500 might look at the crew of the generation ship the same way we look at medieval peasants. The crew will realize that they have spent centuries crossing the void to plant the flag of a civilization that has been dead for half a millennium. The customs they practiced, the language they spoke, the political ideals they were sent to preserve, all of it will be obsolete. They are carrying the ashes of the past into the future. And there is a darker, even more tragic possibility hiding within the mechanics of the generation ship. Suppose the ship leaves, and it travels at 10% of the speed of light for 300 years. In that 300 years, humanity on Earth does not remain stagnant. We continue to innovate. We continue to push the boundaries of physics. What happens if, 200 years after the generation ship leaves, scientists on Earth finally discover a way to bypass the speed of light entirely? Perhaps they invent an antimatter drive capable of reaching 99.99% of light speed, or they discover a method of folding spacetime, allowing instantaneous travel through a wormhole. The Earth could build a new, faster ship. They could launch it, and it could arrive at the destination star system in a matter of weeks or months. When the original generation ship finally arrives, after 500 agonizing years of travel, after generations of sacrifice, disease, and the psychological trauma of living in a steel box, they will look out their windows and see a thriving, fully established colony. They will arrive to find the descendants of the people who stayed behind, living comfortably in gleaming cities on the very planet the generation ship suffered for centuries to reach. The crew of the generation ship will have sacrificed their entire lineage for absolutely nothing. They will have endured 5 centuries of darkness, only to arrive as irrelevant, tragic artifacts of an older, slower era. This scenario highlights the cruelest aspect of the cosmic trap. The universe does not reward effort. It does not care about your sacrifice. It only obeys the math. Whether you travel fast and let time dilation sever you from your loved ones, or you travel slow and let generations of isolation sever your descendants from human history, the result is exactly the same. The void between the stars acts as an absolute quarantine. It ensures that any civilization attempting to spread across the galaxy will inevitably shatter into a million disconnected pieces. The vast distances and the unyielding laws of relativity guarantee that an interstellar empire is a physical impossibility. We cannot rule the stars because we cannot communicate with them in anything resembling real time. If you establish a colony 10 light years away and they experience a crisis, their distress call takes 10 years to reach you. Your response takes 10 years to get back. You are not managing a colony, you are talking to a ghost 20 years in the past. The isolation is absolute. But this isolation forces us to confront an even more terrifying philosophical question. If communication across the stars takes years, and if different observers moving at different speeds experience time at different rates, then we have to ask a question that seems almost absurd to a human mind. If I am on Earth and you are on a spaceship 10 light years away, what exactly is happening right now? In our daily lives, right now is a shared reality. When a news anchor says an event is happening live, we believe it is happening at the exact same moment we are watching it. But in the deep physics of relativity, Einstein destroyed the concept of live. He proved that right now does not actually exist. In our daily lives, we treat the concept of now as a universal truth. We believe that if we could somehow freeze the entire universe in a single instant, we would see everything that is happening everywhere at that exact moment. We imagine the universe as a giant loaf of bread, and now is simply the flat, thin slice we are currently passing through. We assume that even if we can't see a distant planet, there is a definitive, objective reality happening there right this second. But Albert Einstein's most unsettling discovery was that this thin slice of now is a total fabrication. There is no universal present. There is no cosmic right now that we all share. To understand why, you have to look at what physicists call the relativity of simultaneity. Imagine you are standing in the exact center of a very long, high-speed train. At each end of the train, there is a light sensor. Suddenly, a bolt of lightning strikes both ends of the train at exactly the same time. Because you are sitting at the midpoint, the light from both strikes reaches your eyes at the same instant. You conclude correctly that the two lightning strikes were simultaneous. They happened at the same time. But now imagine I am standing on the platform outside, watching your train scream past at near light speed. From my perspective, I see the lightning strike both ends. But because the train is moving forward, you are literally rushing toward the light coming from the front strike and moving away from the light coming from the back strike. From my stationary perspective on the platform, I see the light from the front strike reach you first, and the light from the back strike reach you a fraction of a second later. Here is the part that breaks the brain. Neither of us is wrong. There is no true answer to whether those lightning bolts hit at the same time. To you, they were simultaneous. To me, they were sequential. And the universe supports both of our realities with equal mathematical conviction. Your now is a different slice of the bread than my now. If this seems like a minor technicality, consider the Andromeda paradox. Suppose you are walking down the street on Earth. At this very moment in your reference frame, what is happening in the Andromeda galaxy, 2.5 million light-years away? Perhaps an alien commander is launching a fleet to invade another star system. Now imagine you turn around and start walking in the opposite direction. Because you have changed your state of motion relative to Andromeda, your slice of the universe has tilted. By simply turning around and walking at a brisk pace, your version of now in that distant galaxy has shifted. The alien fleet that was currently launching in your first reference frame might not even exist yet in your second. By changing your speed by just a few miles per hour, you have shifted the present moment of a distant galaxy by days or even weeks. This leads us to a terrifying physical conclusion called the block universe. If my now can include events that you consider to be in the distant future, and your now can include events that I consider to be in the past, then the only logical conclusion is that the past, the present, and the future must all exist simultaneously. Think of the universe not as a movie playing on a screen, but as a solid block of glass. In this block, every moment that has ever happened and every moment that will ever happen is already etched into the geometry. Your birth, your first breath, this exact moment you are living right now, and the moment of your death, they are all equally real, equally permanent, and already there, at specific coordinates in the four-dimensional structure of spacetime. In this view, time does not pass. There is no moving spotlight of the present. Instead, we are like characters in a book that has already been written. Our consciousness is simply sliding through the pages, one by one, experiencing the story as if it were unfolding in real time. But the ending is already printed on the final page. The future isn't something that hasn't happened yet. It is just a place in the block that we haven't reached. Einstein himself grappled with the cold, deterministic weight of this reality. When his lifelong friend Michel Besso passed away, Einstein wrote a letter to Bezos' family that remains one of the most haunting passages in the history of science. He wrote, "Now he has departed from this strange world a little ahead of me. That signifies nothing." For us believing physicists, the distinction between past, present, and future is only a stubbornly persistent illusion. It is a beautiful thought, but it carries a dark, existential sting. If the future is already there, then what becomes of free will? If your path through spacetime is already a fixed world line etched into the fabric of the universe, then every choice you think you are making, every tomorrow you are planning for, is already a historical fact from the perspective of the four-dimensional block. We feel like we are the masters of our time. We feel like we are making progress, moving forward and building a future. But relativity suggests that we are actually passengers on a fixed track. We are moving through a landscape that is already finished. And as we look further out into the cosmos, we see that the universe itself is stretching this illusion to its absolute breaking point. It isn't just that our now is different from an astronaut's now. It's that the very expansion of the universe is pulling the fabric of time apart, making some parts of the cosmos age at a rate that mocks our understanding of history. Because out there, in the deep voids between the galaxies, the trap of time dilation isn't just about moving fast or sitting near a black hole. It's about the scale of the universe itself, and the realization that the further we look into the dark, the more the universe is running in a slow motion we can never hope to catch. For the majority of our exploration, we have focused on the individual. We have looked at how your motion through space or your proximity to a heavy mass can warp the rate at which you experience reality. We have treated time dilation as a personal tragedy, a disconnection between two twins or an astronaut and their family. It feels like a localized phenomenon, something that happens in the extreme corners of the universe, near the speed of light or the edge of a black hole. But as we pull our perspective back, past the star systems and the nebulae, and look at the universe in its entirety, we realize that time dilation is not just a local anomaly. It is the very heartbeat of the cosmos. The universe is not a static, finished stage. It is an expanding, stretching fabric. And this expansion is performing a theft of time on a scale so massive it makes the black holes look modest. In 1929, Edwin Hubble made a discovery that fundamentally altered our understanding of our place in history. He realized that the galaxies were not sitting still, they were rushing away from us. And more importantly, the further away a galaxy was, the faster it was receding. At first, we thought this was simply motion. We thought the galaxies were like shrapnel from an explosion, flying through a pre-existing space. But Einstein's equations revealed a deeper truth. The galaxies aren't moving through space in the traditional sense. Space itself is being created between them. The fabric of the universe is stretching. Imagine a rubber band with two dots on it. As you pull the ends of the rubber band, the dots move apart. If you were an ant sitting on one of those dots, you would see the other dot moving away. Not because it is running, but because the medium it sits on is expanding. Now think about what happens to a wave of light traveling across that stretching rubber band. As a photon travels from a distant galaxy toward Earth, it has to cross billions of light years of expanding space. While the light is in flight, the space it is traveling through is physically stretching. This stretching of space acts on the light wave itself, pulling it out, making its wavelength longer and its frequency lower. By the time that light reaches our telescopes, it has shifted toward the red end of the spectrum. This is cosmological redshift. In the late 1990s, two independent teams of astronomers, the Supernova Cosmology Project and the HiZ Supernova Search Team, were using this redshift to measure the history of the universe. They were looking for a specific type of cosmic event, a Type 1a supernova. A Type 1a supernova is what astronomers call a standard candle. These explosions are remarkably consistent. They always occur when a white dwarf star reaches a specific, critical mass, and they always explode with roughly the same amount of energy. Because we know exactly how bright they should be, we can use them as cosmic mile markers to calculate exactly how far away a galaxy is. But when the astronomers looked at these distant explosions, they noticed something that didn't just change our understanding of space, it confirmed our deepest fears about time. They found that these distant supernovae were fading in slow motion. We know exactly how a Type 1a supernova should behave. We know the curve of its brightness, how long it takes to reach its peak, and how long it takes to fade into the dark. It is a biological certainty of physics. In our local neighborhood, these explosions take a few weeks to play out. But for supernovae billions of light years away, the process was taking much longer. From our perspective on Earth, these colossal, violent events were unfolding in a sluggish, drawn-out crawl. This is cosmological time dilation. It is the ultimate proof of Einstein's reality. Because those galaxies are receding from us at such immense speeds due to the expansion of space, the universe is collecting a velocity tax on a grand scale. The light traveling from those explosions is not just being stretched in color, the entire sequence of the event is being stretched in time. A star that exploded in a matter of days from its own perspective is appearing to us as a slow-motion catastrophe lasting months. When Saul Perlmutter, Brian Schmidt, and Adam Rees won the Nobel Prize for this discovery, they revealed that the universe's expansion is not slowing down, it is accelerating. Something we call dark energy is pushing the universe apart faster and faster. And as the expansion accelerates, the time dilation between us and the rest of the universe grows. The further we look into the past, the slower the universe seems to run. We are looking back at a history that is physically lagging behind our own clocks. But this realization leads to an even more unsettling conclusion. If time dilation is happening on a cosmic scale, then the question we have been asking for a century, how old is the universe, is fundamentally flawed. We are told the universe is 13.8 billion years old. We arrive at this number by measuring the expansion rate and working backward to the Big Bang. But as we have learned, age is a measure of proper time. It is the time recorded by a clock that has lived through that history. And in a universe governed by relativity, no two clocks have lived through the same history. The universe is not uniformly 13.8 billion years old. It is an ocean of varying depths, where time has been running at thousands of different rates since the beginning of everything. Imagine two clocks that were both created at the exact moment of the Big Bang. One clock spent the next 13.8 billion years sitting in the deep, empty void between the galaxy filaments, a region of space where gravity is almost non-existent and the fabric of spacetime is perfectly flat. The other clock spent that same history sitting in the center of a massive galaxy cluster, surrounded by the crushing gravitational weight of 1 trillion stars and the invisible pull of dark matter. Because of gravitational time dilation, the clock in the galaxy cluster has been ticking slower for billions of years. If you were to bring those two clocks together today, they would disagree. The clock from the void would read a much higher age than the clock from the cluster. The 13.8 billion year figure is just an average, a representative number based on our specific perspective in the cosmic microwave background. But for the particles sitting in the gravity wells of supermassive black holes, or for the photons screaming across the expansion of the void, that number is meaningless. Parts of our universe are genuinely, physically younger than others. There are regions of space that have experienced billions of years less history than we have, even though they started at the same moment. The universe is a chaotic patchwork of different ages. It is a tapestry where the threads of time are of varying lengths, all woven into a single, beautiful but incoherent whole. We like to think of the Big Bang as a single starting gun, after which the entire universe began to age in unison. We imagine a vast, cosmic birthday that we all share, but relativity tells us that the universe doesn't have a single birthday. It has a trillion local birthdays. This is the ultimate scale of the trap. It isn't just about an astronaut missing their family. It's about the fact that we are drifting in a sea of asynchronous time. We are isolated from the rest of the cosmos, not just by the vastness of space, but by the fact that the further we look, the more the clocks of the universe diverge from our own. The light arriving at our telescopes today from the furthest reaches of the observable universe is carrying a message from a time that is fundamentally incompatible with our now. We are trying to read a story where every page is written in a different tempo. And as the universe continues to expand and the acceleration increases, these gaps will only widen. Galaxies that we can see today will eventually move away from us so fast that their light will never reach us again. They will be moving faster than light speed relative to us, not because they are traveling through space, but because space is being created too quickly between us. When that happens, those galaxies won't just disappear from our view. They will effectively leave our timeline forever. They will enter a region of the block universe that we can never, ever interact with. The trap will have become total. So we are left standing on a small, rocky planet, holding onto our local clocks with a desperate intensity. We measure our seconds, we plan our futures, and we mourn our pasts. We treat time as if it is ours, as if it is a steady, reliable resource we can count on. But as we have seen, time is a phantom. It is a ghost of the geometry of the universe. It is a flexible, stretching thing that mocks our desire for consistency. Where does that leave us? What is the final takeaway for a species that has finally figured out that its most precious resource is an illusion? The answers are not found in the equations. They are found in the choices we make with the local time we have been given. Because while we cannot change the rules of the universe, and we cannot escape the trap of relativity, we can finally see the universe for what it actually is. It is time to look at the one-way door we are all walking through, and realize that while the rate of our journey is negotiable, the destination is not. We have spent these hours dismantling the most fundamental comfort of the human experience. We have taken the steady ticking clock that has governed every civilization, every war, every romance, and every scientific discovery in our history, and we have revealed it to be a phantom. We have looked at the math of Albert Einstein and the precision of atomic clocks, and we have found that the universe is not a shared stage where we all move in unison. It is a fragmented, warped, and deeply lonely collection of individual timelines, each running at its own pace, governed by the cold, indifferent geometry of mass and motion. This is the reality of the trap. For most of us, the consequences of relativity will remain invisible. We will live our lives at the bottom of Earth's gentle gravity well, moving at speeds so insignificant that our clocks will stay synchronized to within a few billionths of a second. We will grow old together, we will experience history together, and we will die together. In the small, quiet corner of the cosmos we inhabit, the illusion of a universal now is strong enough to sustain a society. We can plan for tomorrow because we know that everyone else's tomorrow will arrive at the same time as ours. But the moment we decide to truly embrace our nature as a species of explorers, the moment we try to leave this cradle and reach for the stars, the trap snaps shut. We have spent centuries romanticizing the idea of interstellar travel. We have viewed the vast distances between the suns as a simple barrier of energy and engineering. We thought that if we could just go fast enough, the galaxy would be ours. We failed to realize that speed is not a gift from the universe. It is a trade. The universe will give you the stars, but it will charge you the lives of everyone you love. Every hour you spend pushing toward the speed of light is an hour that the Earth spends running away from you into the future. You are not just traveling through space. You are paying for that distance with the history of your species. You are embarking on a journey of chronological exile. Imagine the first explorers returning from a mission to a distant star. They will step out of their ships, physically youthful, their minds filled with the wonders of another world. But they will find themselves standing on a planet of strangers. They will be walking archives of a forgotten time, carrying the language, the values, and the memories of a world that has long since evolved past them. They will be separated from the rest of humanity not by miles, but by centuries. And as we have seen, there is no way to turn back. Time dilation is a one-way door. The universe allows you to skip the future, but it offers no path back to the past. You can spend your future more slowly than the rest of the world, but you can never reclaim a single second that has already passed. Once you step out of sync with the human timeline, you are gone forever. This is the existential weight of relativity. It tells us that our existence is not just a matter of where, but of when. To be human is to be part of a shared temporal flow. It is the ability to look at someone else and know that you are both experiencing the same moment, the same era, the same chapter of the cosmic story. Time dilation threatens that connection. It suggests that if we ever truly become a spacefaring civilization, we will no longer be a single humanity. We will be a collection of isolated pockets of time, drifting through the dark, each aging at its own rate, each becoming more alien to the others with every light year crossed. But perhaps there is a quiet beauty hidden within this terrifying math. The fact that time is so easily warped, the fact that it bends around our planet and stretches under our satellites, serves as a constant reminder of how deeply we are integrated into the fabric of the universe. We are not separate from the stars. We are made of the same atoms, governed by the same geometry, and subject to the same relentless laws. The next time you use a navigation app on your phone, remember the 31 satellites hovering in the dark above you. Remember that their clocks are ticking faster than yours because they are further from the Earth's mass, and slower than yours because they are moving at thousands of miles per hour. Remember that if a group of engineers hadn't accounted for the strange, beautiful reality of time dilation, you would be lost. The very infrastructure of our modern world is a monument to the fact that time is not what it seems. And the next time you look up at the night sky, look past the beauty and see the truth. You are looking at a graveyard of light. The photons hitting your eyes right now left those stars years, decades, or centuries ago. Some of those stars might not even exist anymore. They might have collapsed or exploded long ago, but their light is still traveling through the warped geometry of spacetime, carrying a message from a now that has already passed. The universe does not show us the present. It only shows us the history it has allowed to reach us. We are small, fragile beings living in a universe of staggering complexity. Our intuition tells us that time is a steady, reliable river. The universe tells us that time is a flexible, stretching dimension that responds to our every move. We can fight against this reality. We can try to find loopholes in the math, or we can simply accept it. Accept that your time is your own. It is a finite, precious resource that belongs to your specific world line in the four-dimensional block of the cosmos. You cannot borrow more from the past, and you cannot bargain with the future. You can only choose how to spend the seconds you have in the reference frame you inhabit. The trap is real, the isolation is guaranteed, the one-way door is always open. But as we stand here on this small, blue planet, moving together through the dark at 1 second per second, there is a profound meaning in our shared now. For as long as we stay here, we have each other's time. We have a shared history. We have a common present. And in a universe that is actively trying to pull our timelines apart, that shared moment is the most valuable thing we will ever possess. We dream of the stars. We dream of the future. We dream of breaking the limits of our biology and our planet. But as we reach for those dreams, we must never forget the price. Because the universe is waiting in the dark and its clock never stops. It just ticks at a different rate for everyone. The journey into the deep dark is a journey into the future. It is a journey into loneliness. It is a journey into the geometry of a trap that has been set since the beginning of time. But for tonight, our time is still synchronized. Our clocks are still in agreement. We are still here together in the same sliver of the block universe. And for now, that is enough. If you've spent this time with us, exploring the boundaries of reality, consider taking one final action in our shared present. Like the video, subscribe to the channel, and join the conversation in the comments below. It is the only way we can stay connected as we continue to drift into the unknown. Good night and cherish your time, because once it's gone, even the stars can't bring it back.